Hello, in this short video, I'm going to introduce ways to measure data volume, CPU time, and CPU clock rate in a computer system. All right, so here's the outline of the lecture. First, I'm going to introduce the measurement units of data volume. Then we're going to talk about the difference between execution time and CPU time for a given computer process. Then I'm going to define and explain CPU clock rate and CPU clock cycle time and the difference and the relationship between the two. Then I'm going to introduce the classic CPU performance equation. And finally, we're going to see the definition and some examples about CPU clock cycles per instruction. All right, so in order to measure data volume, we need to use some measurement units. In this course, we are using these measurement units that you see in this table. Normally, we are using the binary versions, which are represented by these letters. I'm going to go over them quickly and tell you what each symbol and each measurement unit means. But in some cases, we also use the measurement units that you see in this column. These are a bit more popular and they're used like more commonly by everyone, but we are use them less often in this course. In this course, we basically use the measurement units in this column more, right? These are more popular for this course, but most of most people are used to the measurement units that you see in the second column. Let's find out the difference between the two. The first one, I'm going to start from the very first row. In the very first row, you see kilobyte, which basically means 1,000 bytes. You see the abbreviations and the symbols, I don't want to explain them in detail, but you can see it in the table. And 1 kilobyte is basically equal to 1,000 or 10 to the power of 3 or 10 cube bytes. When we say bytes, we mean 8 single bits. So 1 kilobyte is equal to 1,000 byte, or 1,000 times 8 would be 8,000 bits. So all of these values that you see here are in bytes. If you want to convert them to bits, you need to multiply them by 8. This is the decimal term, which is very popular and very common, but in this course we mostly use the binary version of that, which is called kibibyte, right? And it is shown with this symbol, KIB. The small I between K and B shows that this is the binary version, and the value is a little bit more. It's to the power of 10, which is 1024 bytes. So 1 kibibyte is like 24 bytes more than a kilobyte. This shows the percentage of this shows how much larger kibibyte is compared to its decimal equivalent. Then the second row, you see megabyte and megabyte. Maybe megabyte is 1,000,000 bytes. Megabyte is 2 to the power of 20 byte, which is around 1,050,000 bytes. The next row is gigabytes, which is going to be 1 billion bytes, or 10 to the power of 9 bytes. The binary version is called gigabyte, represented by GIB, and that's basically equal to the power of 30, which is around 1,070,000,000 bytes. And then we have some other bigger, measurement units for volume, like terabyte, petabyte, exabyte, zettabyte, and yottabyte, and their corresponding binary terms like tebibyte, pebibyte, xbibyte, zebibyte, and yobibyte, but these are very rarely used, and you don't really need to memorize them. The first three rows are the common measurement units that are used normally by people and by me during this course. So make sure to memorize the first three rows of this table. The next topic I wanted to cover in this lecture is the difference between execution time and CPU time. It's important that you know the difference between the two. Execution time of a process, a computer process, is basically the total time it takes for the CPU and input-output devices and memory and operating system to do their job and do different tasks for that process to get executed completely. So the execution time is the total delay of a process, which is made of multiple components. What we care more about in this course is the CPU time or CPU execution time, which is basically only a portion of the execution time. It's the actual time the CPU is spent computing a specific task. That's a more specific way for us to measure the performance of a computer system and a CPU. That's specified. So basically, the CPU execution time specifies the CPU performance. That can be divided into two components as well. You can say the CPU time can be divided into user CPU time and system CPU time. The CPU sometimes spend time on the program that you as programmers write, and sometimes it spends time to execute kernel, which is basically the operating system, and its system calls. Like, for example, when you want to print something on the screen, the CPU will spend some time to handle the output devices and basically runs some system calls written in the operating system level. So it's important that we know CPU time is not only the time that the CPU spends on the programs that we write. It's also include the time it spends on the operating system and the kernel level instructions and system calls. All right, the next topic is CPU clock rate and CPU clock cycle time. Every CPU has a clock, which is basically a periodic signal, looks like this, and it's kind of like a sine wave, and it has a constant period, and the period of this periodic signal is called a clock cycle time, or tick, or clock tick, or clock period, or simply we call it cycle or clock. This time is usually very, very small, and we usually represent the time using picoseconds or nanoseconds. 1 nanosecond is 10 to the power of -9 seconds, and 1 picosecond is 10 to the power of -12 second, which is a very, very, very a small measurement unit for time. And CPU clock cycle time is very important because it determines the CPU performance, and it appears in many of the formulas related to CPU performance and the whole computer system performance. Uh, Also, for CPU, we have another quantifier, which is called the clock rate. Clock rate is the opposite or the inverse of the clock period. Clock rate are normally represented as hertz. Hertz means 1 over, or clock rates are measured using hertz, which means 1 hertz means 1 over a second. Um, and normally a clock rate of a CPU is in the order of gigahertz. Giga means 10 to the power of 9 hertz, right? So basically, as an example, we can say the clock rate of a CPU is 4 gigahertz, right? That basically means in 1 second, it will have 4 billion ticks, right? Because, as I said, clock rate is the inverse of clock period. You can convert clock rate to clock cycle and vice versa. Clock cycle to clock rate. All you need to do is to divide 1 by clock cycle to get the clock rate, or divide 1 by clock rate to get the clock cycle. All right, so here is a very simple formula to measure CPU performance. The CPU performance can be measured in different ways and with different formulas. The simplest of them is this simple formula, which says if you want to measure the CPU time or CPU execution time for a program, all you need to do is to calculate the CPU clock cycles that we need, or the number of CPU clock cycles that we need for a program, and then multiply that by the clock cycle time of the CPU. Clock cycle time of a CPU is always constant, and that's going to be 1 over clock rate. If you replace the cycle time by 1 over clock rate, then you get the next formula, which basically says the execution time is equal to the number of cycles that the CPU needs to run a program divided by clock rate. All right, in order to understand the formulas I showed you better, let's see this example and let's solve this example. It's a very simple numerical problem. It says our favorite program runs in 10 seconds. I'm just gonna highlight the numbers that are given on a given computer. Let's say computer A. The clock rate of computer A is 2 gigahertz. And then it says we're trying to help computer designer to build a computer, let's say computer B, which will run this program in only 6 seconds. So we're going to enhance the performance from 10 seconds. We're going to drop the execution time to only 6 seconds. The designer has determined that a substantial increase in the clock rate is possible. However, it will increase this increasing clock rate will affect the rest of the CPU design, causing the computer B to require 1.2 times as many clock cycles as computer A needs for this program. The question is, what clock rate should we tell the designer to target? So this is a problem that can be solved in a step-by-step fashion using the formula that we saw in the previous slides. I'm going to start by converting this clock rate for computer A to clock cycle time. So we know that the clock rate of A is equal to 2 gigahertz. 2 gigahertz means I'm sorry. Let me erase this. 2 gigahertz means 2 billion hertz. So that's equal to 2 times 10 to the 9 over a second, because a hertz is 1 over a second. And therefore, the cycle time for computer A is going to be equal to 1 over this, which is going to be 1 over 2 times 10 to the power of 9 second, which is going to be equal to, if you simplify this, that's going to be 0.5 nanosecond, right? So that's what we know for now regarding computer A. And then the program runs in only 10 seconds. So given the formula that we had earlier, the total time is 10 seconds. That should be equal to the number of cycles that we need for the program that is our favorite program, uh, times the cycle time, which is going to be equal to 0.5 nanosecond, right? And given this equation, you can calculate the uh, number of cycles that we need, that it takes for this program to be executed. And that would be equal to 10 over 0.5 nanosecond, which if you can simplify it, you get this number. Number of cycles would be 20 billion. So it would be 20 times 10 to the power of 9 cycles, right? So that's the first thing that we get. Now, it says if you want to change the design and change the computer and create a computer B, then it needs 1.2 times as many clock cycles as computer A. So computer A already takes 20 billion cycles, right? If computer B needs 1.2 times more, how many cycles does computer B need to run this program? In order to answer that, all I need to do is to multiply this number, 20 billion, by 1.2 to get the uh, number of cycles for computer B. So all I need to say is a number of cycles that I need in computer B is going to be equal to 1.2 times 20 billion, which is going to be 2.4 times 10 to the power of 10 cycles, right? That's the calculations. And the question is, what clock rate should we tell the designer to target? In order to answer this part, all I need to do is use the same formula that I used earlier and say, because the goal is to get the 6-second CPU time, 6 should be equal to, I know how many cycles I need or it takes for computer B to run the program. That's going to be 2.4 times 10 to the power of 10, and I'm just going to divide this by the clock rate. If you remember, number of cycles over clock rate is going to be equal to the execution time or CPU time. So if you want to if you want to find out what the clock rate for processor B is, all you need to do is to solve this equation. So clock rate of B should be equal to 2.4 times 10 to the power of 10 over 6, which is going to be equal to 4 gigahertz. Giga means 10 to the power of 9, so it's going to be 24 over 6 times 10 to the power of 9 hertz, which is going to be 4 gigahertz. All right, so now that you know the very simple formula for measuring the CPU time, it's time to make it a little bit more complex or a little bit more realistic. As you remember, in the formula that we had for CPU time, we had the term called CPU cycle time, CPU clock cycles. That means we needed to find out how many cycles, how many clock cycles the CPU takes to run a program. This is always not given, so you need to calculate it yourself. In order to calculate the total CPU clock cycles for a given program, you need to know two different quantities. One is how many instructions I have for a program. That can be calculated using like different methodologies. If you know the way the program is written, it is possible to find out how many instructions we need for that program. So if you know this, you only need one other quantity to calculate the CPU clock cycles, and after that you can calculate the CPU time. And that quantity is the average clock cycles per instruction. That's a very important factor and property that a CPU architecture has, and we call that CPI. That means the CPI, or the average clock cycles per instruction, is defined as the average number of cycles that a CPU needs to execute one single instruction, right? So the average number of clock cycles per instruction for a given program in a given CPU is called CPI, right? And now that we have this formula which says the CPU clock cycle equals number of instructions times the clock cycles per instruction, we can create a better formula for the total CPU time. All we need to do is, in the formula that we see earlier, we're going to replace the CPU cycle time by the product of number of instructions for a program times the average CPI, and that's going to give us the complete formula for the total CPU time. All right, so combining the formulas that we see in the previous slides gives us this very nice and important formula, which says the CPU time equals the number of instructions that a program needs to be executed times CPI, number of cycles per instruction, times clock cycle time. If you remember, this part gives us the number of cycles that a program needs to be executed. So that's going to be the number of cycles. And you multiply this by clock cycle time to calculate CPU time. Or you can just move this part into the denominator and consider it as clock rate, because clock rate and clock cycle time have an inverse relationship, right? So it's easy to get to one formula given the other. That's not a big deal. In order to illustrate the formulas that we saw before, let's look at this very simple example. Let's say we have two implementations for the same instruction set architecture. That means we have like two different CPUs or two different computers. They both have the same instruction set, and that means they understand the same language. Computer A has a clock cycle time of 250 picosecond, and the CPI of 2, that means the number of cycles per instruction, the average number of cycles per instruction for computer A is 2. Right? That means one instruction can be calculated or can be executed in 2 cycles on average for computer A. For computer B, the numbers are different. The cycle time is 500 picosecond, the CPI is 1.2, and the question is which computer is faster for this program and by how much. The point is the numbers that are given are for the same program. So it says for some program A has some CPI, for the same program B has some other CPI, right? And we know their clock cycle time. So in order to simplify things, I'm going to assume that this program has an instruction count equal to IC for both architectures, for both A and B. right? So when I write IC, I'm referring to the instruction count of the program in both computers A and B. So what I'm going to do is I'm going to find out the total execution time or CPU time of computer A to run this program, and I'm going to calculate the CPU time of computer B to run the same program, right? So we're going to measure these. If A's CPU time is less, A is faster. If B's CPU time is less, B is faster, right? It's a very simple question. Which one is faster? The one that takes less time to run the program. So let's do that. I'm going to start with program A. Instruction count. If you remember the formula, instruction count times CPI times the clock cycle time, which is 250 picosecond, right? If you simplify if you multiply and simplify this, that's going to be equal to 5 times 10 to the negative 10 times IC, right? Or instruction count. For computer B, we have the same instruction count. The CPI is 1.2, and the cycle time is 500 picosecond, which is going to be equal to 6 times 10 to the power of negative 10 times IC. Please note that, when I'm doing these calculations, I know 1 picosecond is 10 to the power of negative 12. So if you simplify it a little bit, you can get the numbers that I got, right? So this is, sorry, let me raise a little bit, yeah. So that's equal to 10, right? Okay, so which one is faster? A. Why should I say A is faster? Because A takes less time. This quantity is less than this quantity. Therefore, A is faster. So just to summarize, the total time that it takes for a CPU or a computer to run a program is going to be equal to the number of instructions that the program has times the number of cycles it takes for the CPU to run or execute each instruction times the number of seconds or the amount of time it takes for the CPU to do one tick or one clock cycle, right? And the measurement units for each piece or each quantity is as follows. For the CPU execution time for a program, the measurement unit is in seconds, right? The instruction count has no specific measurement unit because that's basically the number of instructions that are executed for the program. The clock cycles per instruction, which is going to be the CPI, is defined as average number of cycles per instruction, and that's always a constant number without any specific measurement unit. And then the clock cycle time is in seconds. If it's in nanosecond or picosecond, you can convert it back to second by just multiplying it by 10 to the power of negative 9 for nano and negative 12 for picosecond, and that's how you can use the formula that I mentioned in this lecture. Finally, I'm going to list the components that affect the performance of a computer program in a computer system. The algorithm that we use to write a computer program can greatly affect the performance of a process. The programming language that we use to write the program will affect the performance. The compiler that we use to convert that language into a low-level language understandable by computer hardware is another piece, another component that affects the performance greatly. And finally, the instruction set architecture. So in this course, we are going to see or we are going to focus only on um, the last three. We are not going to see anything about the algorithm, which affects greatly the performance, but I'll do my best to uh, make sure that you understand the um, importance of programming languages, compilers, and instruction set architectures in performance of a computer program.